Okay, hello. In this lesson, this is probably the sixth, maybe fifth, sixth, seventh part of a lesson where we're looking at regressions. We're looking at taking some data, entering it into our calculator. We're going to do a linear, quadratic, and exponential regression. We're going to figure out which of those three is the best. It's kind of like a shirt. You look at three different models wearing that shirt. Maybe one model looks better than the other. Okay? In these three cases, we have the shirt, the t-shirt, the data, and then we're going to try it on three different models, three different humans, or three different models, all right? And we're going to figure out which model is the best. Using that, we're going to make predictions. All right, so here we go. I'm going to first enter this data into the calculator. All right, so I grab my calculator. You can do it with me. Turn the calculator on. You're going to hit Stat, Edit. Then whatever is there, come over on List 1, go up to the very top, and don't press Delete. Do not press Delete. Instead, you press Clear. So I hit Clear, and now if I arrow down, it wipes out. What happens if you accidentally come up here and you press Delete on L2? If I press Delete, notice List 1, List 3, like List 2 is missing. Alright? So I want to make List 2 reappear. So in order to make it reappear, I hit Stat, come down to Setup Editor, I press Enter. Enter again, it says Done. So I come back to Stat, Edit. List 1 is here. List 2 is now here. It was the one that we deleted a moment ago. So that's how you make it reappear. Anyway, List 2, I'm going to hit Clear and arrow down, and it clears out. Now, I'm going to enter in my data. This is the X and the Y values. That's List 1 and List 2 respectively. So on the video, I'm going to pause the video right now, and if you're working on it, you can pause it yourself. All right? Go ahead and enter this data in, and then we'll start the video again. Okay, so I have entered the data now. Here it is in my calculator. Now I'm going to use this to be able to try out the three different models, linear, quadratic, and exponential. So let's do that. We're going to start off by pressing Stat, arrow over to Calc, arrow down to the number 4 option. A lot of people make a mistake and come down to the 8th option, which is also a linear regression, but that is the wrong one. We want X plus B. We want slope-intercept form. So we come here. Linear regression, AX plus B. That's the same thing as X plus B. So we select number 4. This menu comes up on the TI-84. Okay, List 1, List 2. Come down here to where it says Store Regression Equation. You're going to press VARS, which is right here. VARS by pressing over. Function, so I hit Enter. And Y1, so I hit Enter. Now I'll arrow down to where it says Calculate. And I'm going to press Enter. Y equals AX plus B. That's slope-intercept form. And what is the R value? R equals 1. Quadratic. Let's do the exact same thing by pressing Stat, arrow over to Calc, arrow down to the 5th option, Quadratic regression. So it should be X list is list 1, Y list is list 2. Store regression equation. Right here, we're going to press what buttons? Vars. What's next? Y vars. What else? Function. What else? Y1. Okay, just do Y1 on all these. So now, right here, calculate, we hit enter. Okay, so it gives me an R squared value equal to 1. What happens when we take the square root of R squared? I'm sorry, what happens when we take the square root of R squared? Okay, so when I take the square root of R squared, I get R. And the square root of 1 is 1. I can do that. I can do the square root by hitting second and then the x squared button right here, the square root of 1. I hit enter and it gives me 1. Alright, so now it's time to look at the exponential regression. I press stat, arrow over to calc. I'm going to arrow down to the 0 option. It's xreg, exponential regression. Select enter. Okay, L1 L1 and L2, that's X list and Y list. Now the store regression equation, what do I put there? Put Y1. How do I get to Y1? Vars. Y vars. Function. So I'm going to press enter. Y1. Press enter.
Wait, so it's always going to be Y1?
It's always Y1. So I select enter for calculate, and it gives me an R value here of 0.9944. Okay, next step. What's the best regression, what's the best model here of these three? These are the same, right? They're both 1. But linear is an easier equation to work with than quadratic, right? It's more simplified. So we're going to choose linear. And then the next step, we're going to write in the equation. Y equals. And what is that linear equation? It's not here because this is the exponential equation.
Wait, so how do you know that it was linear?
So both of these have an R value that's equal to 1, and that's the best it can get, right? So I'm going to select linear because a line is just easier to work with than a parabola, right? Line versus a parabola. You know, that's why you learn about lines before you learn about parabolas. Okay, so we're just going to work with this. Since this is a tie, it goes to the easier model. All right? Now, so we're going to write down our equation, but we got to get the linear equation back up here. Can you do that for me? Can you figure out what buttons to push? We've done the exact same thing 3 times to get the linear, the quadratic, and the exponential models. So how do we make this? We're going to press stat. What else?
Or would you go over to calc?
We'd go over to calc. Then what?
Number 4?
The 4th option. Press enter.
Then go down to the rating.
Yep, list 1, list 2 is good. So we came down to store regression equation.
Then press bars. Then Y bars.
So vars, y vars, function y1. Come down to calculate, hit enter. And there's the equation. It's in slope-intercept form. Y equals mx plus b, where the m is actually a, but that's the slope. it's 0.45, 45, 45, and it continues forever. But for our purposes, we're just going to round it on our paper to be 0.45. And then that's going to be times x plus b, which is 1. So now I'm going to go ahead and start answering questions. According to your model, what would the medicine dose be for a 210-pound man? So let's be clear about this. We're talking about, if I was to make a sketch of this, we were to look at someone's weight versus the dosage. What do you think is going to be true? As you get someone who's heavier and heavier, they'll need like a larger and larger dosage, according to this table here. So as it turns out, it actually happens to be in a straight line, the information, the data. It's in a straight line. So let me ask you, should we give like toddlers the same medicine dosage like that we would give a 20-year-old? No, right? It'd probably kill the toddler. That would not be good. So instead, we give them a smaller dosage, and this makes sense. You know, the older or the bigger someone gets, they get a larger dosage. All right. So, according to your model, this is the model, the linear model. According to your model, what would the medicine dose be for a 210-pound man? And then it's going to ask for a 110-pound man, or a 150-pound man. So how do you do this? Well, in previous lesson, I showed you the steps. I gave you some notes, and I told you that the last part of this you would be answering questions and making predictions. Typically, the questions revolve around me giving you an X and you find the Y. But let me ask you in this case, what is X and what is Y here? The weight is X and the medicine dosage is Y. So right here, what am I giving you in this question? Is this X or is that a Y value? That's an X value. So here, X equals 210. So what we put into our calculator will look like this. Y1, parentheses, 210, close parentheses. This equals, I'm going to type this into my calculator right now, just like I see it, Y1 of 210. Now, how do you get Y1? Well, you're on the normal screen, on the home screen. Make sure you're there. If you're not sure where you're at and you just want to get there, you can always press second, quit. Okay, home screen. And now I want to type in Y1. So I hit vars, yvars, function Y1, parentheses, 210. Press enter, and I get 95.45. And I'm just rounding to the nearest whole number. Okay, so what's pretty crazy here is we have different weights that are given, ranging from 88 pounds all the way up to 187 pounds. 187 pounds, that's given. And what we did is we just entered in 210, and we made a prediction. Please watch this. We made a prediction that lives outside of this table. 210 is beyond this table. Like, we've given from 88 to 187, but we want to make a prediction about 210. Like, how much medicine should we give a 210-pound man? And the answer is going to be found on our, right here. It's 95. Okay? So I'm just making a sketch of my problem here. There's my line. And I just made a prediction about, for a 210-pound man, I should have a medicine dosage of 95 milligrams. Do you guys understand that? Like, it is important for us to be able to know how much medicine is appropriate for a 95-pound man. For a 210-pound man. And that medicine dosage should not be the same amount that I give a toddler that weighs only, 20 pounds. Okay, so let's go ahead and do this next part. For a 150-pound man, that is an X value, so I'm going to do the exact same thing, Y1 of 150, and get that Y value. So I plug in 150. Here it is. I press vars. I arrow over to yvars, function, y1, parentheses, 210, close parentheses, hit enter. Oh, shoot, I just did the exact same problem. I wasn't thinking when I was doing it. So, by the way, a shortcut to do all that is to press second and then the enter button, and it brings up the last entry. So now I can arrow over and change 210 to be the correct number, 150. Hit enter. So, a 150-pound man will take less medicine than a 210-pound man. Does that make sense? 68 milligrams. Okay, next question. Does the model give a more accurate estimate for the medicine dose for a 210-pound man or a 150-pound man? I'm going to take a highlighter real quick. 150-pound man. 150 pounds lives basically right here, right? Somewhere there. Yes or no? The problem is that information isn't given. What can you probably say is true about how much should we be giving a 150-pound man? Well, it should be less than 70, and that's exactly what we came up with when we actually did the problem, 68. We found out exactly 68 milligrams is how much we should enter for a 150-pound man. But 210, where does 210 live on this table? It lives off the chart. That's exactly what I wanted to hear. 210 lives off the chart. So how much should we give them? Well, we came to the conclusion that was 95 milligrams. Okay? Now, let me ask you something. Can we count on, and this is important, can we count on our answer of 68 milligrams for a 150-pounder or 95 milligrams for a 210-pounder? Can we count on one of these answers to be more accurate than the other? What do you say? Both should work just fine? Okay, maybe. Anybody else got a thought about that? Say again? Close enough. Okay, that's fair.
The single milligram
a single. Okay, so here's what I'm going to say. There's two concepts here known as interpolation and extrapolation. Interpolation and extrapolation. Interpolation is predicting a value that lives within the table that's given, the data that's given. Extrapolation is predicting a value that lives outside, extra. So look, the data that was given ranged in weight from 88 to 187. 210 doesn't live in, it's extra. Does that make sense? 210, we had to go outside of the table. So anyway, this is extrapolation. This is interpolation. My point being is that you can always count on interpolation to be more accurate than extrapolation. I say always, but I guess there's maybe situations where that's not true, but I'm thinking that it is. It makes sense. You with me? Predicting values that live within the data given is easier than predicting values that live far beyond what's already given. For example, if I wanted to predict the gas prices in 5 years from now, is that really possible? Let me ask you this: can I predict the gas prices 2 days ago, or maybe even 5 years ago? Yeah. But can I predict the gas prices for 5 years from now? I could, but do you believe that that will be 100% accurate?
You can only have your best good.
Because what's possible? What could possibly happen in the next 5 years? I'm thinking a couple things. We could either maybe find maybe another. Sorry, for a second. Yeah. So what could happen in the next 5 years with gas? One thing that could happen is maybe we find an alternate source of energy that can replace gas. For instance, there's all kinds of research being done on in order to fuel a car. In order to propel a car, they've looked at trash, being able to take trash and somehow dump it into some sort of box in your car, and it like squeezes it and it uses up stuff in your trash to turn that into fuel in order to move your car. Or what if what if they are doing some research and they find something that exists maybe in the bottom of the ocean, and we've got just so much ocean out there. All we got to do is just somebody's got to go and harvest that, and then sell it.
Effort and
Maybe,
money.
but see, the thing is that if we have that instead of gas, then maybe it would reduce.
Dangerous too.
Maybe,
I'm just saying. They've done that before.
So the point being, guys, is that whether you find something in the ocean, or trash, or potatoes, or coffee, or whatever it might be, would that or would that not reduce the gas prices? It would reduce the gas prices. So, as we roll on here, let's finish answering this question. Does the model give a more accurate estimate for the medicine dose of a 210-pound man or a 150-pound man? What is your answer? 150. And why is that? Because it falls within the data values given. It falls within the given data. So how would a linear, quadratic, or exponential model make more sense in the context of the problem? So in this particular problem, we chose linear because the R value. But let's throw out the science. Let's throw out the R value for a moment. Is there any reason why we should go with a quadratic or an exponential model for this problem? Is there anything that suggests we should? I don't think so either. The answer is no. Line is good. Now lastly, do we need to make any restrictions on the domain of this equation to make sure that it's a good fit? And I say no, but I'm not a doctor, so maybe there's more information that I need to take in before I can make that with an absolute fact. Okay, so once again, we're just trying to look at more and more examples of regressions and the types of problems that we can do with them, making predictions based upon those regressions. So I'll probably have another video or two left, but I know that this is getting close to the end of my video series here. So what I would say is if you're stuck on any of the concepts that you see here, I would suggest that you go back to a previous video, a previous lesson. Start with part 1 and work your way up. All right. So thank you for watching and have a good day.